So next, let's look at ionic compounds. Ionic compounds are usually a metal with a nonmetal. We'll explore a little bit further and talk about polyatomics and some other combinations that form ionic compounds. They're always charged components. Remember when we talked about ionic compounds, we said that they were formed because of ions, right? Transfer of electrons. So when you're approaching a chemical formula, how do you identify it as an ionic compound? Well, if you're looking at the periodic table, I'm not talking about polyatomic ions, you just look at the elements present in the formula. So we have calcium, which is an alkaline earth metal in that fuchsia or pink color. And then we have that attached to chlorine in this chemical formula. And chlorine is a halogen, so it's way over in the nonmetal portion. So metal in a nonmetal, that tells me it's ionic. When it's ionic, I have a different way to name them. So I'm no longer going to be using prefixes if the compound in question is ionic. So how do you name ionic compounds? Well, of course you have to start by figuring out if the bonds are ionic or not. And we just looked at how to do that. If they are ionic, we need to see, well, are there polyatomic ions involved? We also need to ask ourselves, are the metals involved, do they have multiple charges? Meaning, are transition metals involved? So ionic compounds can become very difficult to name because there's a lot of metals on the periodic table to take into consideration. But we're going to start out slow with a standard naming system for binary compounds. Remember that word binary means 2 elements only. Then we'll move on to talk about polyatomics and the transition metals. Let's look at naming binary ionic compounds. If you look at the 3 examples above, you know that all of them are ionic because we always have a metal with a nonmetal. Also notice, the metal always comes first. So we have sodium, an alkali metal, the first element present in the first compound. We have magnesium, which is an alkaline earth metal, and then potassium. So it's always metal and then the nonmetal portion. We are not going to use prefixes, so forget about them. No mono, di, tri, tetra, anything. When we name them, we're simply going to take the first element, straight off the periodic table, no special ending. That's going to be the metal portion, the cationic portion, the positive ion. Then the second element present, which is the nonmetal, we're going to put the element name with just an IDE ending. So we are still going to use IDE endings like we did for covalent, but we're not going to use a prefix. Now the nonmetal portion is usually the anion because they gained an electron from the metal portion, making them negative. So here is the basic systematic naming. You name the positive ion first, which is most often a metal, not always, but most often. The second element present, the negative portion, you use its name, but with an IDE ending. So let's start out with NaCl. The metal portion is sodium. So you would just find that on the periodic table and write the name exactly how it appears on the table. For the second portion, it's chlorine. And since it's the negative ion and the second one present, we're going to add an IDE ending to that to become chloride. Next, we have Li2O. Now notice there are 2 lithiums, but does this matter? Well, it matters in the sense that yes, there are 2 of them, but it doesn't matter for naming purposes. We're not going to be using prefixes, no di, tri, nothing like that. So instead, we just look at the symbol, in this case Li, realize it's lithium, write that name down. The second element present, oxygen, will have an IDE ending and become oxide. KBr, finding K on the periodic table, is potassium. Then we have bromine, which becomes bromide. Last but not least, Ca, calcium. Cl, chlorine, but since it's the second element present, chlorine becomes chloride. Notice there are two chlorines, but we didn't say dichloride. Now let's look at going the reverse way, much like we did with the covalent compounds. So we're going to be writing chemical formulas based off of the name. So it's a little more difficult with ionic compounds to take the name of the ionic compound and come up with the formula. Because since we aren't using prefixes, it doesn't tell us how many atoms of each we need to put. So how do we figure it out? Well, we can figure it out because we know what charges the main group metals form in ionic compounds. Those are listed in the periodic table to the left. So how you would start this, if I'm giving the compound magnesium bromide, what I would do is I would find both magnesium and bromine on the periodic table and write down their corresponding charges. Magnesium is an alkaline earth metal. Notice it's going to form a +2 when it's an ionic compound. So I write magnesium with a 2+. So what ion does bromine form? Well, it's a halogen, so it's going to form a -1 ion by gaining 1 electron. Next, what I need to do is make the compound neutral. What does that mean? Well, magnesium bromide is an ionic compound, yes, but the compound itself overall is neutral. And if I had just one magnesium and one bromine, that would not make a neutral compound because I have a +2 charge and a -1 charge. If I add those together, it's not going to equal 0. So what do I need? I need another bromine. If I add another bromine, now I have two -1 charges, which would give me a total of -2. That is going to neutralize my +2 charge, which is on the magnesium. So my compound would be Mg1Br2. I would need 2 bromines to neutralize the +2 on the magnesium. Another way to do this is called the crisscross method. So how do we use the crisscross method? We start off the same way. We take the name of the compound. In this case, we're using aluminum oxide as an example. You would start by finding the chemical symbols and the charges of both aluminum and oxygen. So aluminum has a +3 charge. Oxygen, being in group 16 and having 6 valence electrons, will want to gain 2 more to become a -2 charge. So how does this work? Well, you take the number, so this +3 on aluminum, and that 3 is going to become a subscript on oxygen. The 2 on oxygen, not the charge, just the number, is going to become a subscript after aluminum. So we're crisscrossing those numbers. So the formula that we're going to get is going to be Al2O3. The 2 coming from the charge on oxygen and the 3 coming from the charge on aluminum. Notice we just brought the numbers, not the charges themselves, so we left the positives and negatives alone. What that means is I need 2 aluminums for every 3 oxygens in this compound. What we're showing here is just that the method does work and that it is a neutral compound. So we just said we have 2 atoms of aluminum. Each of those atoms has a +3 charge. Given this chemical formula, that subscript of 3 says that we have 3 oxygen atoms, and we know that each of those oxygen atoms are going to have a -2 charge. So what we're trying to check is that it is indeed neutral. So if we have 2 atoms of aluminum at a +3, that's going to give me +6 on the plus column side. I have 3 atoms of oxygen, each with a -2, so that's going to give me a -6 on the oxygen column. A +6 plus a -6, they cancel each other out. That compound is overall neutral. When you are using the crisscross method, you do need to make sure that you're using the smallest whole number ratio. So if you can simplify it down, do so. I will be showing some examples in class where you'll see this. example shown here is if I took calcium, which has a +2 charge, and oxygen, which has a -2 charge. Now, if I do the crisscross method, I get Ca2O2. Well, notice this can be reduced down further. If I divide both by 2, I will simplify it to just CaO, where I have 1 calcium per every 1 oxygen atom. So now let's look at naming ionic compounds if a polyatomic ion is involved. And in order to do that, we need to know what a polyatomic ion is. So polyatomic ions are ions, meaning charged components, charged compounds, that consist of 2 or more atoms. Now, the atoms in the polyatomic ions are bonded covalently, but the polyatomic ion itself has an overall charge, whether it be a positive or a negative charge. Since it has a positive or negative charge, it is used as either a cation or an anion in ionic compounds. So off to the right here, I have a list of common polyatomic ions that we'll see present in some of the compounds we're going to be naming. I do want to point out that most of them are negatively charged, or anions, so they're often going to take the place of the non-metal portion. There is one on this table that has a positive charge, NH4+. That is the ammonium ion. So since it has a positive charge, it's going to take the place of the metal portion, the cationic portion of the ionic compounds we've been naming so far. Another thing I want to point out is a lot of these names are similar. So let's look at the last two in the table. We have SO4 with a 2- and SO3 with a 2-. So notice they only differ by 1 oxygen. When you're looking at their names, the names themselves, sulfate for SO4 and sulfite for SO3, only differ by 1 letter. So be very careful when you're naming these compounds, because even just 1 letter difference or 1 oxygen difference can make the answer go from right to wrong. Let's look at some examples. When we name these, we're going to be naming them just like binary ionic compounds. We're going to start with the cation portion, and we'll name that straight from the periodic table. Now with the anion portion, the polyatomic portion, we'll find the polyatomic ion on the table and use the name given on the table. So we're not going to add any IDE endings when a polyatomic ion is involved. So how do you know if a polyatomic ion is involved? Well, looking at this first example, I would know one's involved because there's more than 2 elements present. I have Sr, strontium, I have carbon, and I have oxygen. So I have 3 elements present. So that must mean there's a polyatomic involved somewhere. So the Sr portion, strontium, we would find that on the periodic table and just write its name exactly how it is on the periodic table. The rest of it, the CO3, we would look it up in the polyatomic table, see that CO3 has the name carbonate, and write that name down. So strontium carbonate would be the correct name for that polyatomic ionic compound. Let's try a few more. So another clue showing that an ionic compound has a polyatomic in it is if there's parentheses. So whenever you see parentheses around it, that means that that is a polyatomic. The number outside of the parentheses is saying how many of that polyatomic ion are present. In this case, 2. So how do we name it? Start with the metal portion, strontium. NO3 being a polyatomic we would find on the table, and NO3 has the name of nitrate. Does it matter that there is 2 of them? No, because this is an ionic compound and we're not using prefixes. Next we have Al2SO4 sub 3. Once again, parentheses alert me to the fact that there's a polyatomic involved. So Al is aluminum, SO4 we would find on the table, and it is sulfate. So the name for that compound would be aluminum sulfate. Now in this next example, you might notice at first that there's no metals. Another thing you might notice is that there are 4 different compounds listed, or 4 different elements listed, excuse me. So since there's no metal, that gives me a clue that this first part is probably a polyatomic. And it is. It's our only positive polyatomic on this table, ammonium. When you're naming a compound with 2 polyatomics, simply write both names down, starting with the first one present. So this would be ammonium, and then the NO3 portion, nitrate. Here are some more examples. Now we're going to take the names of ionic compounds and come up with the chemical formulas. Now we looked at that already with the magnesium bromide example and the aluminum oxide example. So whenever you're approaching a problem like this, the first thing you want to do is find the element symbol of both atoms or polyatomics involved and their charges. So what I have shown here is the first step. I have written down both elements involved in each example along with their charges. Notice when we get to the polyatomics. How do I know it's a polyatomic? Well, the first 3 examples have IDE endings. That's because when we name binary ionic compounds, we add an IDE ending to the second element present. So I know that nitride is really just nitrogen. Bromide is really just bromine. However, the last 2 examples, I have an ATE ending. So this alerts me to the fact that it's probably a polyatomic. So I would look at the polyatomic table, find nitrate, and write it down exactly how it appears. NO3 with a -1 charge. Same with sulfate. Well, now how do you come up with the chemical formulas? You can do the crisscross method, or you can line them up until the charges cancel and the element is neutral. For instance, this first one, potassium has a +1, chlorine has a -1. Do those charges cancel? Yes, they do. So what that means is I only need one of each to make a neutral compound, so my formula would be KCl. Now I'm going to skip down to aluminum sulfate, the last example, because I'll work on these during class. With aluminum sulfate, I'm going to use the crisscross method this time. So I have 3+ charge on aluminum and a 2- charge on the sulfate. So how do I come up with the chemical formula? That 3 is going to become a subscript on the SO4. The 2 is going to become a subscript on aluminum. So I'm going to get Al2 and then SO4 sub 3. Now the trick with polyatomics is if I have more than one of them, I want to make sure to put parentheses around that entire polyatomic, and then I'm going to put the 3 on the outside of those parentheses. We'll work on more of these in class. Now it's time to look at the last type of ionic naming compounds. So it's the stock naming system, and this is with transition metals. So far, all of the examples that we've looked at have been with main group metals. We've been using alkali metals, alkaline earth metals, and aluminum. Now we're going to look at the D block, the transition metals. So all of those numbers in blue, all of those elements in blue. So all transition metals have variable charges. What that means is we can't predict what its charge is based off of where it is on the periodic table. For instance, iron, it can have a +2 charge or a +3. Copper can have a +1 or a +2. Cobalt, a +2 or a +3. There's no rhyme or reason to it just by glancing at the periodic table. There's a deeper way to figure this out. So how are we going to figure it out? Well, given this example, FeCl3. So I would identify that as an ionic compound because iron's a metal and chlorine is a nonmetal. But I can't just name it iron chloride and be done with it. Why? Because the metal involved is a transition metal. And since the transition metals can have multiple different charges, I need to somehow indicate when I'm naming it which ion it is. Is it the +2 iron or is it the +3 iron? So how do I do that? I do that by using Roman numerals. So if, for instance, this is the +2 ion of iron, I would write iron and then Roman numeral 2. If it is the iron 3+ ion, I would write iron and a Roman numeral 3. So how do we figure out which ion it is just by looking at the chemical formula? Well, you're going to start with the one you know. So we just said, I don't know what iron is. What is the charge on it? Is iron +2 or is it iron +3? Okay, well, since I don't know what the charge is on that, let's look at what it's attached to, what it's bonded with. So this iron is bonded with chlorine. And I do know what the charge on chlorine is. Chlorine's a halogen. It's number 17 here. And halogens always have a -1 charge. So if I know that chlorine has a -1 charge, well, how many chlorines do I have? The subscript tells me that. I have 3 chlorines. So what's the total negative charge that I have? Those 3 chlorines tell me I have a total charge of -3. So what I need is for this chemical formula, this compound, to be neutral. I know it's neutral because there's no charge on it when it's in its chemical formula. So if I have a -3 charge on the anion side, what charge do I have to have on the cation side to cancel out that -3? I'm going to have a +3. So what that tells me, since there's only one iron atom, is that that iron is the +3 iron. Now that I know which ion it is, I can name my compound. So I'm going to name it by writing iron, Roman numeral 3, chloride. When you are writing these, you don't have to put parentheses around the Roman numeral. That's just my personal preference. So now we're just looking at the 2 examples we would see with the 2 different iron ions and what those would look like. So you can see iron has 2 different ions, iron 2+ and iron 3+. We just saw the example, iron 3 chloride, where the corresponding chemical formula was FeCl3. Well, what would the chemical formula look like for iron 2? Well, that's right next door. Iron 2 chloride would be FeCl2. Notice we are adding the IDE endings just like we did when we named other ionic compounds. Here are some examples that we're going to work through in class. So we're going to name the compounds shown here with these chemical formulas, and then we're going to take the names and convert those into chemical formulas. So in summary, we have 2 different types of bonds we've talked about, ionic versus covalent. For covalent bonds, we often see metals and nonmetals, but we will also see some examples when a nonmetal and a metalloid are combined. For ionic, there's many more different types. We have a metal and a nonmetal, which is the simplest form, especially if it's a main group metal. We saw metals with polyatomic ions. We can also see 2 polyatomics together, or a polyatomic with a nonmetal.